there's a space curve. Now, as a point goes around that space curve, it traces out a path in space, but I mean, it's not going in a straight line, so the x direction and the y direction and the z direction are changing as it goes around. If they're changing, then they have a derivative. They're changing with respect to time. That's what we're looking at now. We want to see that if I'm at a particular point on this space curve, how is the x component changing? How is the y component changing? How is the z component changing with respect to time? We're going to take the derivative of the space curve. When we put those three derivatives together as the components, what we're getting is a tangent vector. So if I've got this space curve, there's going to be a vector that's tangent to that curve that shows you the instantaneous direction that that particle is moving as it goes around the curve. And that instantaneous direction is the direction of that tangent vector. The length of that tangent vector is going to be how fast it's moving, if we're thinking about it as a particle moving around that space curve. Let's get to the mechanics of it. So here we've got a function, r. The x component, the y component, the z component, they're all functions of time. So the vector itself, that vector function, is a function of time. That point in space is given by a function of time. If I want to know what the derivative of the vector function is, we could put it into the definition, the derivative definition that we used in single variable calculus. You'll remember that limit as h approaches 0 of f of x plus h minus f of x all divided by h. It was the secant slope, and we took the limit as the 2 points got closer and closer together. The limit of the secant slope was the tangent slope. That's the same idea that we're doing here. If we do this then, so now I'm taking this limit and I need the function. So this 1 over h, let's take that to the outside here. H is going to 0. And we've got this function with t plus h plugged in. So t plus h plus h plus h. Now I'm showing it in 3 dimensions. It works in any dimension, minus the actual function here, the actual. So this should all be in one giant bracket. So there's our limit definition. Now if I put this vector minus this vector and divide each piece by h, let's just look at the one component, because I think that'll make it clear. So the first component is going to end up being, the first component has the f in it. So I'm not going to worry, the rest are the same, so dot 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 with the other 3. Let's just look at one piece and see what happens. Now the limit as h approaches 0 of this component. Well, that by definition is the derivative of the function f with respect to time. So that first component is going to be, I'll use this notation here, df dt. So actually this works just like you would think it would work. The derivative of a vector function is just take the derivative of each component separately with respect to time, and that gives you the tangent vector. So let's see this in an example here. So find the derivative of the function. So here's a point, here's a vector function, and if I want the derivative, I'm going to write it like this d. I could write it as r prime, but to be a bit more clear, I'm going to write it as the derivative of the function with that vector with respect to t. So I'm taking the derivative of the first function. The derivative of cosine is minus sine. I'm taking the derivative of the second function. I'm taking the derivative of the third function. There's the derivative. It's a vector function. The derivative of a vector function is a vector function. And this vector changes. I mean, the x component goes up to 1 and down to -1. The z component doesn't change, though. That's like a constant, the slope is constant in the z. So the z is always 3t. The z component is always increasing, and it's always increasing at the same rate, 3. You let 2 seconds go by, it goes up 3 meters, let's say 3 meters per second. So find the derivative of the function. That's not too bad. That's mechanically very straightforward. We can use it in other types of questions here. So find the tangent vector to the function. So here's a function. We want the tangent vector, and we want it at the point 3, 4, 6. So the tangent, let's get the tangent vector first. So that's going to be r prime. Now it's not ambiguous when I say prime. There's only one independent variable, the t. So when I say r prime, we know it's the derivative with respect to time. So I'm differentiating the first component, I'm differentiating the second component, I'm differentiating the third component. So I just took the derivative of each one of these pieces separately. And there's our vector. But it's not a constant vector, it's a function, it's got t in it. We want the tangent vector at this point, 3, 4, 6. First off, this curve goes through the point 3, 4, 6. Yeah, when t is equal to 2. The x component is 3, the y component is 4, the z component is 6. So saying at the point 3, 4, 6 is the same thing as saying when t is equal to 2. So now I know when it goes through that point. I have the derivative. I can just plug in t. So in the notation, let's write this in some good notation. That would be r prime at 2, evaluated at 2. There's only one place to plug the t in, here. So there's our tangent vector. That vector, the curve is going through space, and that's the vector that's tangent, that's giving me the direction right when I'm at that point, right at t equals 2 seconds, let's say. And that vector has a length, and that length is going to tell us how fast it's moving if I'm thinking about a particle carving out that space curve. So here's our other questions. What about a unit tangent vector? Now, have a vector. If I wanted to make it a unit tangent vector, I need to scale out its length. So I need to know what's the magnitude of this vector. So I'm looking at the magnitude of this vector, how long that vector is, and that's just the square root of the first component squared plus the second component squared plus the third component squared. So what's that? That's root 26. So that's how long this vector is. I want a unit vector parallel to this 1, 4, 3 vector, but only 1 unit long. So our unit vector is going to be equal to, I'm just going to end up dividing by, I'm going to scale it down. I'm going to divide each component. So that's going to be 1 divided by root 26. Four divided by root 26. And 3 over root 26. Put that up here. And it's a vector, so let's put our vector hat on it here. It's a unit vector that points in the direction of the tangent vector. Now the tangent vector had 2 pieces of information. A vector has 2 pieces of information, direction and magnitude. So this tangent vector was telling us the direction that the curve was moving at that particular instant, the tangent vector, and its length was giving us like a a measurement of how fast, if I'm thinking of it as a particle moving through space. By making it a unit tangent vector, I've scaled out the length, and I've only got the pure direction. So there's the pure direction that the curve is moving. It's still a tangent vector, but it's a unit tangent vector. Now, next question then wants to know, what's the tangent line? So if I want the tangent line to a curve, what do I need for equation of a line? I need a point and a vector. I have a point, 3, 4, 6. I just need a vector. I could use the vector 1, 4, 3, or I could use the unit tangent vector. It doesn't matter. I'm going to use the vector 1, 4, 3 because it doesn't have divided by square root of 26 in it. So the tangent line, I'm going to make the vector equation of a line is equal to the point, and I'm writing it like a vector so that I can add vector plus vector, plus a constant, that's our one-dimensional parameter that we can change, times the direction vector. There's our equation of the tangent line, vector form. So actually tangent line is it's a rather straightforward question. It's a good test question because it figures out if you can make the equation of a line. It figures out if you can take the derivative of a space curve. It's got answers to things in one question. Before I move on though, a common error that I sometimes see is that people will take the direction vector here, but they'll leave the t in it. It'll be 2t. The direction vector of a line is supposed to be a constant. So there should be only that one parameter in here. A line is a one-dimensional straight object. Oh, straight object. What's the tangent vector to a line? Well, if I differentiate this, I'm going to make this I'm going to take the derivative with respect to its parameter. Here the curve's parameter was t. I keep talking about it as time because that's easy for us to imagine. But in this case, it's a space curve whose parameter is k. So if I took the derivative of this function, it would be with respect to k. And the derivative with this function with respect to k would just be the constant 1, 4, 3 vector. Yeah, the tangent vector to a line is just a constant vector, just like the slope of a line in 2D is a constant number. As an example on this curve, think about this is our point here, and at that point, the curve bends, but at that point it's going in this direction. So that would be the tangent vector. At this point, it's going in this direction. That would be the tangent vector there. At this point, it kind of looks like it's going out this way. That would be our tangent vector. So as the point goes around, the tangent vector is changing. So now if I'm taking derivatives, that looks sort of super straightforward. We're going to make some general rules about functions of vector functions. And let's look at what if our function is the dot product of two vectors. So let's say u and v. If I'm dot producting u and v, and I'm showing it in 2 dimensions here, our dot product works in any dimension. But if I've got these two vectors whose components are all functions of time, and I dot product it, first times first plus second times second plus third times third, now if I were to take the derivative of the dot product, I'm just differentiating these. It's a function of time. This ends up being just a scalar function of time. Yeah, it's not a vector anymore because you plug in a dot product just gives you a number. Here you plug in t, you get a number plus a number plus a number. The end is a number. So if I'm differentiating this, I'm going to use product rule on each of these little pieces. So what I mean is, if, for instance, let's just say g of t was equal to the dot product. So it's a function of time. It just happens to be the function is take the dot product of those two vector functions. And I were to differentiate g, so g prime, no ambiguity, the g prime means taking the derivative with respect to t, that's the independent variable. It would be differentiate this piece here, but that would just be doing product rule on the first piece, which would be take the derivative of the first, I'm doing product rule, derivative of the first, leave the second alone, plus leave the first alone, times the derivative of the second. That's my derivative of this piece. Now I have to add to it the derivative of this piece. So that's going to be derivative of the second. Product rule again. Derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. All right, so those two pieces are the derivative here. Now there's one more piece to take the derivative of, and I mean, you see the pattern with this. It's going to be product rule again. Undo. So I'm going to take derivative of the first, leave the second alone, plus leave the first alone, times the derivative of the second. So there's three pieces here. Each piece splits up into two because product rule gives you those two pieces. So I should have 6 pieces here. There's my derivative of this vector function. Now, we can rearrange some things. This is the answer, but I want to make a more general rule. So all the things that have the u primes, that's this one. I'm going to move this one over. And here's another u prime. I'm going to move that one over. So here's all the ones with the u primes. Here's all the ones with the v primes. Notice that this is u prime, no v no prime, u prime, v no prime, u prime, v no prime. And here it's u no prime v. But okay, long story short, where I'm going with this is this piece looks like the u vector primed. So that looks like I took the derivative of the u vector and dot producted it, took the dot product of it with just v. This second piece looks like I took u, left it alone, and dot product did it with the derivative of v. So this is where I'm going with this. If I'm taking the derivative of this dot product, it looks, I mean, dot product is kind of like the multiplying, it's one version of multiplying vectors together. So you think when you're taking the derivative of this product of vectors that you would use something that would look like the regular product rule, and it totally works. It's derivative of the first, dot product, leave the second alone, plus leave the first alone, dot product, derivative of the second. That works just like you think it should work. All right, if that's true, what about if my function is not the dot product of two functions, dot product of two vector functions, but the cross product of two vector functions? So what if now it's a function, and I'm going to take the derivative of that. It works exactly like you think it works. The cross product is just like another product. You hope it works like the regular product rule, and totally, except for those are cross products. So, and now I'm not proving this, I haven't proved it yet. It only works in 3D because the cross product that we know is a three-dimensional formula. If I did want to prove this, I would brute force this out with the product rule formula, and then take the derivative, and then collect terms together, and see that left side is equal to right side. That would make like 15 minutes of boring video watching me do algebra. It would be better, or the other thing I could do is say, pause the video and do this yourself. Yeah. You know what? If you want to, you should. But even if you don't, this is the rule. You really should. Lastly then, a chain rule. Oh, wait, no. Let's figure this out first. This when I take the dot product, so I want to make a comparison here. When I take the dot product of two vectors, I get a number. So the dot product of two vector functions is a scalar function of time. When I take the cross product of two vectors, I get a vector. So the cross product of two vector functions is itself a vector function. So when I take the derivative of it, it's a vector function. So maybe we should I'm going to emphasize that that's a scalar function of time. Spell it right. Scalar function of time. And this cross product is a vector function of time. Their derivatives are, so they're scalar functions and their derivatives are scalar functions. They're vector functions and the derivatives are vector functions. All right, let's look at this last rule here. Instead of being a vector that's a function of time, it's a vector that's a function of a function, f, that's a function of time. So each component is a function of f, and f is a separate function of time, and I want to take the derivative of that. Now the rule's going to work, actually the rule's going to work like you think it works. It should be like chain rule. So if I'm differentiating this, so I'm taking derivative of the whole thing, that would be, if it was chain rule, I would take derivative of the outside, leave the middle alone, multiply by the derivative of the inside function. And that's how it works. Oh, is this a vector function or a scalar function? Well, this is a vector, and I'm taking the derivative of a vector, so I'm getting a vector. This f prime is a scalar, but I'm multiplying it through the vector. So the answer in the end is a vector function. Let's do an example of that to see the mechanics of it. So here I've got a two-dimensional vectors dot product. So I can't use this as an example for the cross product. I can only do it for the scalar function. I'm taking the derivative of g prime. So I'm taking the derivative of g, that's g prime. And it's going to be, all right, it's supposed to be the derivative of the first. So I'm going to write it in a unusual way. Dot product, leave the second alone. Plus, leave the first alone times the derivative of the second. I'm following this rule here. Now let's take the derivative of the first vector. The derivative of sine is cosine. The derivative of t squared is 2t. I'm still then dot producting against this, leave that vector alone. Gotta have a dot product in the middle. Plus, now I'm leaving this first alone, and I'm taking derivative of the second. The derivative of 3t minus 2 is 3. The derivative of ln t is 1 over t. Oh, note to self, this second vector is a vector function, but the domain what t's I'm allowed to put in. I can only put in positive t's. Can't plug 0 time in. Can't plug negative time in. So anyway, here's our. Now I got to clean it up. Dot product. So first times first. First times first plus second times second. So that's this dot product, all a scalar function of time. Now let's do the second one. First times first plus second times second. T squared times 1 over t is just going to be equal to t. So there's our derivative, scalar function. There's g prime as an example. Now, that's using this rule. We could have just dot producted the whole thing out and then taken the derivative and would have got the same function. So now that might be tempting to say, well, I'm not going to remember these formulas then because I'll just dot product it out and take the derivative like I do normally. Sure, but these formulas will help us simplify things later when we don't have actual functions, when we're trying to use these in proofs in upcoming examples. Let's do one more example. Here I've got a function. The vector is a function of a function. So it's the sine of f and the ln of f. Again, it's two-dimensional. The function that's inside is t cubed. So I want to take the derivative with respect to time. So I'm going to get a vector function. So that's going to be, take the derivative of the outside function, so sine becomes cos, leave the middle alone. The derivative of ln of is 1 over. There's the derivative of the outside function times by the derivative of the inside function. So f prime is going to be 3t squared. So there I'm following this rule. I took the derivative of the outside, left the middle alone, times the derivative of the outside function. It's like chain rule. Now I can clean this up by distributing this into the vector. And I mean I can write this as 3t squared cos of, and now I could, if I want, write what f is. It's t cubed. And this will be 3t squared over t cubed, which would just be 3 over t. So there's the derivative, using the chain rule. Now you totally could just put the t cubed in, then just take the derivative like normal. That also works. You would have been doing chain rule on each piece sort of separately. But knowing these rules, as I said, will help us simplify some of the things later. Coming up, okay, we learned how to differentiate vectors. Coming up, we better learn how to integrate vectors.